Good evening again. It hardly seems like 5 minutes when I was last here talking to you. Okay. So this is JWST+2. The +1 I gave a year ago to celebrate the fact that the James Webb was launched 1 year after Christmas Day in 2021, and now it's almost 2 years on from that point, hence JWST+2. A million miles above midnight, you'll see why that is there in just a moment. So just a very quick reminder, the James Webb, it took an awful long time to build the telescope, but eventually they were happy that it was functioning correctly on the ground, so they folded it up, put it on the top of a rocket and launched it on Christmas Day 2021, and then hoped that it would unfold correctly and then start to work. A reminder again about the basic spec, it's got a segmented mirror, substantially larger than the size of the Hubble, because it's no longer restricted as to having to fit into the cargo bay of a shuttle. They could now put it on top of a rocket with a slightly larger fairing, so they could get away with a larger mirror, but still it needed to be folded, but some 6.5 meters in diameter. Again, a reminder of why you want the James Webb when you've already got a Hubble, because it's working in a different part of the electromagnetic spectrum. So there on the left-hand side, the Hubble Space Telescope is working in the ultraviolet and the visible and a little way into the infrared. The Spitzer Space Telescope is working a long way into the long wavelength infrared, and the James Webb Space Telescope is sitting there in the middle. So the James Webb effectively plugs a gap in between what the Hubble has been doing for 3 decades and what the Spitzer has been doing for quite a few years. I can't actually remember exactly which year the Spitzer Space Telescope was launched. So the James Webb overlaps a little bit with both of those. So some objects have been observed with more than one telescope. So the telescope was launched in late 2021 and was sent to this red dot on the right-hand side called L2. It's a mysterious point in space where you can park a spacecraft and it will basically sit there. And it'll sit there and you'll need very little fuel just to keep a little nudge every once in a while to keep it in the right position. Strictly speaking, not at the red dot, but doing an orbit around the red dot. And the red dot is on the opposite side of the sun. In other words, the red dot is sitting directly above midnight on Earth, because of course the left-hand side of the Earth is facing the sun, so that's local noon, and local midnight is the right-hand side of the Earth. And so the James Webb is essentially hovering 1 million miles above the midnight point on the Earth's surface. And it's out there to keep it as far away as possible from the moon and the Earth and the sun, such that one heat shield can block all of the heat from those 3 objects. Because it's working in the infrared, it's working effectively in heat, and therefore you want to block the heat from the moon, from the Earth, from the sun. One of the reasons for the James Webb existing as an infrared telescope is to look back in time. Because the universe is expanding, light from very distant galaxies has been stretched by the expansion of the universe. So very distant galaxies that might have emitted a lot of ultraviolet and visible light, that light has been stretched into the infrared. And therefore, hopefully, there's quite a large number of galaxies which look brighter in the infrared than they do in the visible. So they should be able to be visible even if Hubble can't see them because they're too faint. It's hoped that the James Webb will be able to see them. And the more distant galaxies, we're looking back in time because light takes a finite time to reach us. So if the galaxies are many billions of miles, many billions of light years away, then it will take billions of years for the light to reach us, and hence we're looking back in time billions of years. So there's now on the right-hand side, the Big Bang, the kaboom, on the left-hand side, and the amount that the light has been stretched is called the redshift. So there's effectively no shift of light that's right next door to us, but the further back in time we go, the more light has been stretched. And what's interesting is this period between the blue lines there, because we're interested in when did the first stars and when did the first galaxies form. We know that there are lots of galaxies around us now, and we know there's lots of galaxies that have been around for billions of years. But when in that little time interval there did they actually first appear? If we blow that up and think about that 500 million years or so, from the Big Bang for the first few 100 million years, stars and galaxies they formed sometime along that bottom line, but we don't know exactly when. And you can see that if we went back to a redshift of 10, meaning the light has been stretched tenfold compared to when it left the galaxy as to when we measure it here, z equals 10 or z equals 14, we're getting further and further back in time. Hubble has already taken us to about there. Hubble has seen to about z equals 7, 8, 9, 10, and that's pushed our knowledge of the universe back to the first 500 million years. It is hoped that the James Webb, if it observes for a while, will be able to take us even further back than that, to the point where maybe we get to the point before the first stars and the first galaxies formed. And there we might be able to see them in the process of formation. That's the hope. So we need to get back to redshift values, ideally much bigger than 10. Bear that in mind for what comes later. After it had been operational for a little while, they checked it all worked, and they took some images and took some spectra, and they were released a few months after the launch. But this is JWST+2, so I'm going to look at what's happened this year, what's happened in the last 11 or 12 months, because I've already talked about what happened in JWST+1. So let's have a look at what's released, not necessarily exactly month by month, but just spaced out over the year. Earlier this year, they released this set of images of a dusky disk. In other words, this is effectively a solar system seen from the side. The star itself has been removed. Normally, the problem is the star itself is so bright, you'll never have any chance of seeing any planets or seeing anything else in that solar system. So they've artificially removed the star. Everything inside the dotted circle has been removed. And what you're left with is the dusty glow of whatever else is in this solar system. Now, it's thought that there's a couple of planets in the solar system. They don't show up in these particular images. But what we are seeing is a whole load of dust in the plane of the solar system. Now, in our solar system, I'm not sure you've ever seen it, but the zodiacal light is the light that's reflected off all of this dust that occurs in the plane of the ecliptic, in the plane of the Earth's orbit. You sometimes see it as a glow of light after sunset or before sunrise, as long as you've got no pollution around. So in effect, we're seeing the zodiacal light of a exoplanet system. We're seeing a distant star. This is a few thousand light years away. And we're seeing the zodiacal light. We're seeing the dust that's formed in addition to the planets that are going around this particular star. And because dust tends to absorb light and then radiate heat, it shows up well in the infrared. It's very difficult to see with any other telescope, for instance, the Hubble. This is only an artist's impression. Don't think that James Webb produces images like this. But accidentally, it found an asteroid of about 150 meters in diameter. It was actually looking for something else, and it was people were looking through calibration images, and they said, what's this extra object in the field of view? It turns out to be an asteroid. What's amazing is not that the asteroid is 150 meters in diameter. We see a number of asteroids that size coming close to Earth. This asteroid was still in the asteroid belt. It's not close to Earth, it's still out there, way beyond Mars, and yet it still managed to find a small object, no bigger than an athletics running track, basically, 150 meters or so across, and it saw it at a distance of the asteroid belt. And that gives an indication of the sensitivity of the system. Hopefully it'll mean that we can see even smaller asteroids coming our way. And remember, that might not be a planet killer, that might not be an extinction level event if that hits the Earth, but 150 meters of rock hitting a city will basically obliterate the city. It won't necessarily kill all of mankind, but it will make a big mess to a big country. So it's as well to be able to see these objects. There are some stars out there, including this one, a so-called SoU3A star. You can see it looks rather almost fluffy, as it were. We think this particular sort of knotted behavior in this nebula is a sign that this star has been blowing material out episodically for thousands of years. This object has been sloughing off part of its outer atmosphere. It looks like it's unstable. It looks like it's coming to the end of its life. it's possible that this is a precursor to a supernova. Maybe this is what stars do before they go bang. This is a very massive star. This is about 30 solar masses, very heavy compared to the sun. And it's been estimated, when you look at the material, that over the last few thousand years, it's probably already shed about 10 solar masses worth of stuff into this nebula, and it might have 10 or 20 solar masses left. And it does look like these sorts of stars are worth keeping a close eye on because they might well go supernova fairly soon. And coming back to the comment in the at the end of the previous talk, we can see all the stars have these characteristic hexagonal spikes on them. That is a consequence of the hexagonal segments and the interface between these segments in the mirror of the James Webb. You can, in principle, take them all out, but they're there, so generally speaking, they're left in the images. We don't always look at the other end of the universe with the James Webb. Sometimes we look very close to home. This is Uranus. Back in 1986, Voyager 2 went past Uranus and saw pretty much nothing at all. It had a fantastic time as it went past Jupiter and Saturn. There was high expectation when it went past Uranus and great disappointment when it saw effectively a completely blank billiard ball, and then it went on to Neptune. But it turns out that maybe we were just unlucky with Voyager. It happened to pass Uranus at a time that not much was happening, because now we realize it is actually a rather stormy planet, as well as having a beautiful ring system, which Voyager was not capable of seeing in great detail. It's also clear that there's something interesting going on the left-hand limb of the planet here. It looks like a big storm system. And the right-hand large patch you can see is actually effectively a pole. Once exposed to the sun, this feature seems to show up, and they don't know exactly what's going on, but clearly the sun, remember the tilt of Uranus is quite extreme compared to the tilt of the Earth. It looks like the storm systems that develop on the planet are very much dependent on which way the pole is pointing compared to the position of the sun. So with a spacecraft, you fly by a planet and you just have to take what you see over a period of a few hours. But of course, now we have the luxury of revisiting by simply asking Webb to go back and take more images of Uranus in the future. We can watch storm systems developing. As well as looking back in time on the cosmic scale, one of the reasons for the James Webb going up and working in the infrared is it can see very dusty environments, and it can see planetary systems that otherwise would be almost impossible to see. So this is Fomalhaut, the brightest star in the constellation of the Southern Fish, and it has already been established that it has a very large outer ring of dust around the star. Again, the star has been removed. The black dot in the middle is the very bright star has been removed to show the rather fainter, dusty environment around it. So the outer ring was already established. Hubble saw that. It's a bit like the Kuiper belt within our own solar system. But what Webb has revealed is that inside the equivalent of the Kuiper belt, there's another ring and another ring. It's as if it's found the asteroid belt of another solar system. Having already established that it's got a Kuiper belt, it's now seen an asteroid belt. You might be tempted to think that if we look in detail at some of these rings, we see a little bump. Is that a planet inside there? Well, it might be, but it's more likely to be just a cloud of relatively dense particles. So just like in the case of, for instance, in the case of Saturn's rings, we see rings with gaps in them because of the shepherd moons. And when we look at our own asteroid belt, we see gaps in the asteroid belt because of the effects, the gravitational tug of Jupiter. It's thought that this system is not just a uniform disk of gas, but actually has these rings with gaps between them because there must be planets there that are shepherding the dust and actually forming rings and gaps and rings and gaps. So we can deduce planets, even if we can't see the individual planets, by looking at where the dust is, which Webb is really good at. We can get an idea of planetary formation. And the more of these sorts of systems that the James Webb looks at, the more understanding we get of how planetary solar systems come to be. In June, this one was an astronomy picture of the day. In June 2023, this is the Pandora cluster. Again, some of this cluster was already imaged by Hubble. It's not that unusual for James Webb Space Telescope to revisit objects that have already been imaged by Hubble, usually at different wavelengths, to see what more we learn. In this case, Hubble has viewed the inner part of this particular cluster of galaxies called Pandora's cluster, but here James Webb has taken a larger field of view by making a mosaic of 4 images to make a much wider field of view. And in only some 4 or 5 hours exposure, they've managed to capture a huge number of galaxies in this cluster. It's been estimated that if you add up of course there's a huge number of galaxies and a few stars in there as well, it's estimated that there are some 50,000 sources of light in this particular image. So again, this is going to keep people happy with their analysis for a long time to come, understanding the dynamics of this cluster, as well as how this cluster is bending light from more distant galaxies as well. And again, having the ability to see further back in time more distant galaxies because they glow brighter in the infrared allows these sorts of images to show more detail. Even though the James Webb has got the same resolution effectively as the Hubble Space Telescope, having the extra sensitivity in the infrared gives us more information. To celebrate its first year of operation, it was launched on Christmas Day. It took quite a few months to calibrate everything and make sure everything worked exactly as it should, make sure each of the segments of the mirror were in exactly the right place to act as if it was one big mirror. And it wasn't until the summer that they actually got the first science. So July of 2023 was effectively the first anniversary, 12 months after the first science releases. So if you like, this is the first anniversary picture. It's a picture taken from the Rho Ophiuchi cloud complex, molecular cloud complex. And Rho Ophiuchi, that's the constellation of Ophiuchus, and Rho is just one of the bright stars in that particular constellation. But you can see there's an enormous amount of stuff going on here. The red is a whole load of molecular hydrogen that appears to be jets that are coming out of early star formation. Early star formation always seems to produce jets via a mechanism which is still being researched. Why is it that when gases collapse from a cloud into a star, you end up getting jets coming out of the star? That is something that's been observed many times, and people are trying to understand exactly what that mechanism is. So here we've got lots of hydrogen, the red, we've got jets coming off left and right, we've got jets going up and down, and we have this huge, almost fluffy yellow cloud in the bottom left, which is a huge cloud, which again is early star formation, and it looks like a very massive star that you can just about make out in the middle there. That massive star is partly lighting up the cloud around it and partly excavating a sort of bubble around it. When I saw that Rho Ophiuchi was the anniversary picture, I thought that's interesting, because a long time ago I tried imaging Rho Ophiuchi, and that is the entire cloud complex. Rho Ophiuchi is the little blue star towards the top of the image, a little triplet star, and as well as the blue nebula, there's a nice yellow nebula and a lot of dark nebula, so that's why it's called a molecular cloud complex, because there's an awful lot going on. And I thought, well, where was Webb pointing? And I looked at my image thinking, I wonder if I can identify where Webb is in there. And then I remembered the focal lengths. My focal length here was a 135 millimeter telephoto lens, about yo big. So my image is 135 millimeters. Webb's image, Webb has a focal length of 135 meters, not 135 millimeters. So Webb's focal length is some 1,000 times bigger. But I thought, what the hell, is it possible to actually identify where that image was taken? And I zoomed into my image there. So there it is a bit bigger. Rho Ophiuchi is that little triplet of stars right at the top of that image. That's the star that's lighting up the rest of this nebula blue. And there's a boundary there between the blue part of the nebula and a dark part of the nebula. And at that boundary, there's a little yellow smudge, which is not more than a pixel or 2 or 3 in my image. That yellow smudge there is the yellow smudge of the Rho Ophiuchi picture from the James Webb. So I think James Webb does a better job than I did. But it's interesting to note that in principle, 1 pixel in my image was actually the object that was the anniversary picture from the James Webb. So I thought that was a nice touch to think, well, you can actually trace from an amateur picture what it is that James Webb is actually doing. In August 2023, so only a few months back now, it imaged the supernova 1987A, the supernova that went off in the Large Magellanic Cloud. That Large Magellanic Cloud is about 150,000 light years away, and this obviously went off in 1987. And the material that's the shockwave of this particular supernova has been expanding ever since 1987. But even before the supernova went off, just like we saw with the Wolf-Rayet star, that particular star was ejecting a lot of material into the interstellar medium, perhaps for many thousands of years, perhaps even 10,000 years before it went supernova. It was ejecting material into the interstellar medium. Then the supernova went off and a shockwave came out at close to the speed of light, and that shockwave has now caught up with the material, and that's why you see this sort of equatorial ring, almost like a string of pearls, lots of little dots. That is the shockwave from the supernova catching up with all the material that was ejected thousands of years ago at a much lower velocity. So it's a very dynamic environment, which is why there's so much interest in studying this, not just taking a snapshot, but studying it and revisiting it every few weeks, every few months, absolutely every few years. Lots of times Hubble has gone back to this to produce a movie of how this shockwave is moving through space. And Webb will pick up the torch, if you like, and continue doing that for years to come to see how this structure made from the supernova shockwave continues to develop in years to come. And hopefully, by looking at that shockwave and looking at that supernova remnant, we'll get, again, more information and more understanding of how supernova go off. In September 2023, astronomy picture of the day was this particular star system. It's again showing jets. Jets seem to be all over the place, and we're really trying to understand why stars form and produce jets, why black holes form and produce jets, why do some galaxies have jets. They seem to be all over the place, not necessarily for the same reasons. And I'm sure there's armies of PhD students all over the world analyzing data, trying to understand what's going on. In this particular case, this is a very early bit of star formation. It's not a star. For instance, our sun is some 4 or 5 billion years old. Some stars only live for millions of years. This star right at the middle, which we can't see because there's so much dust in the middle, this star might only be 10,000, 100,000 years old, very young on a time scale of stars. And right from the center there, coming out from that little dark patch in the middle, there's little spindly jets you can see. And these jets eventually plow into the interstellar medium and produce these shock waves. So it's interesting to note as a dynamic event as to what's actually going on, but also it'll help us understand jets, it'll help us understand star formation. Some people think that early stars have to form jets because of the way a cloud of gas is condensing into a star. It's got to lose the angular momentum somehow, like a skater pulling in their arms. They would spin faster and faster. They've got to somehow get rid of this energy, and it's thought that maybe jets are the mechanism by which inspiraling gas loses some of its spin. On examining the jets rather closely, I can't necessarily see it from here, but I have been told that if you look at the jets very carefully, the jets seem to be the same on both sides, implying that there's a certain symmetry there. And some people believe that if you analyze it carefully, you can deduce that this star actually must be a binary star from the nature of how those jets are being produced. So maybe what we're looking at is the very, very early birth of a binary star. And again, stellar evolution hopefully will progress as James Webb and other telescopes get more and more images like this. In October 2023, so we're now only talking about last month, this particular image of a kilonova was released. A kilonova is the result of probably two neutron stars colliding with each other, producing a huge output of energy. And it doesn't look much in this particular image, just a little red dot in the top left-hand circle, but that particular merging of two neutron stars, each of which might have the mass of the sun, for instance, coalescing into one, produced a huge burst of gamma rays, called a gamma ray burst, not surprisingly. And this is one of the brightest gamma ray bursts ever seen. not only by the James Webb, but by other telescopes around the world. And rather curiously, they have worked out, I guess by looking at the spectrum and other things, they have come to the conclusion that that particular pair of neutron stars that seem to have emerged at the point where the red dot is, they actually originally came from that galaxy, but were kicked out. Now, why they were kicked out of that galaxy, I don't know. It happens from time to time. Galaxies are not stable structures any more than the solar system is a stable structure. Jupiter might decide to kick a planet out of the solar system. Well, in this case, maybe a few stars decided to kick this pair out. Maybe they got kicked out when they first formed. Maybe the original supernova or whatever event that produced these neutron stars, in the process of producing the stars, actually gave them enough of a kick to leave the galaxy. So they've actually left the galaxy 100,000 years ago, and that's why there's a huge distance between them now, the galaxy on the right and the two neutron stars that have merged to produce the kilonova on the left. Somewhat interestingly, one of the things that James Webb has discovered is that if you look very carefully at that, what is assumed to be the merger of two neutron stars, you can see various elements. You normally see some hydrogen, some sulfur, some oxygen, some other elements in there. By looking in detail at what's going on there, the James Webb has found tellurium. Tellurium is element number 52. It is way heavier than iron. It is heavier than copper. It is heavier than silver. So they've conclusively proved that heavy elements, very heavy elements, are made when two neutron stars collide. So it might change our way of thinking, whereby we say, well, any element up to iron has been made inside stars, but any elements heavier than iron have been made in a supernova. Well, maybe, but maybe they're made by two neutron stars crashing into each other, because it looks like that quite definitely makes elements heavier than iron. So again, more studies of these sorts of systems will give us a much better picture of where all of the elements in the periodic table have actually come from. Still October 2023, the James Webb Space Telescope produced a rather lovely image of the Crab Nebula. Similar at first sight to the image produced by the Hubble Space Telescope some 20 or so years ago. But there's actually a lot more going on. I'm still tempted to click the laser, but there's an awful lot going on in this sort of milky area around the outside, as well as the orange, which gives you the structure of the supernova remnant. There's a lot more sort of milkiness. It almost looks like it's not quite in focus, but that's not what's going on. What's happening is that lots of electrons are being generated and are bending in the magnetic field, presumably generated by the neutron star that's at the center of the Crab Nebula, the neutron star that's left after this supernova was generated. And perhaps you can see little wisps that sort of give the impression, a bit like the wisps that you might see in the solar corona. It gives you the impression of where the magnetic field lines are in this supernova remnant. And it's thought that electrons are whizzing around at high energy and being molded by these magnetic field lines, and that's what produces this characteristic radiation. It's called synchrotron radiation. It's what happens when charged particles move in magnetic fields, and that, we think, is what we're seeing there. It's very interesting to compare that with the original Hubble. If I can do this very carefully, that's Hubble, James Webb, Hubble, James Webb, Hubble, James Webb. If you look at one particular feature, just pick on one feature that you can see by eye, you notice that a particular feature is a little bit closer to the center for Hubble than it is in James Webb. Remember, the Hubble picture was 20 years ago. That's now, that's 20 years ago. That's now, that's 20 years ago. It looks like the Crab Nebula is ever so slightly bigger than it was 20 years ago. No surprise there. It went off in 1054, and 20 years is effectively 1/50th of its lifetime as far as going back 1,000 years is concerned. So no surprise that it seems to be a couple of percent bigger. The fact that you can actually see it is rather amazing. And the fact that you've got all of this detail, this milkiness, which isn't really visible in the Hubble, because the Hubble is looking at visible wavelengths and it doesn't show this effect quite as well. But it is nice to see an image with a similar resolution to the Hubble, but giving us different information, and giving us information 20 years later on from the original Hubble image of I think that was 2005 or something around there. The last image from this set, taken from Astronomy Picture of the Day, just as you can see, effectively a few days ago, 10th of November 2023. This appears to be one of the earliest black holes that has been found anywhere. So the James Webb has found a galaxy, and we think that galaxy contains a black hole because a different telescope, the Chandra telescope, shows that X-rays are coming from that particular point in space. So we couldn't necessarily have determined that from the Webb, but the Chandra can simply say there's an object in that direction. The Webb says it's coming from that particular galaxy, and that particular galaxy has a redshift of 10, a Z of 10, meaning the light has been stretched tenfold since the light left this object. So this object has produced this light some few 100 million years after the Big Bang. In other words, we're pushing back that boundary. If you remember the earlier slide, once we get beyond about Z equals 10, we're starting to look at the very early universe. This particular supermassive black hole, it would appear, existed only a few hundred million years after the Big Bang. How do you get anything that big so early is what the astrophysicists are now working on. They know that in a few billion years you can make a really big black hole. But how do you get one that big after only 500 million years or so? And it might well be that having found this one at Z equals 10, maybe if James Webb keeps looking, it'll find more and more supermassive black holes and perhaps stars even earlier to test our theories of how we think stars came to be immediately after the Big Bang. So the James Webb has been very busy for the last 12 months, and I'm sure if I ever get round to writing JWST+2, there'll be equally exciting things to come in the next 12 months. So I wish you all a very Merry Christmas. Thank you.